Hello students, in the last class we discussed some special types of subgroups. We have to show that the intersection of two subgroups is again a subgroup, and we show that the in general union of two subgroups need not be a subgroup, and we show that union of two subgroups is only if one of them is contained to the other. And finally we have to define the center of a group, and then we show that this center of a group is a subgroup of a G. So today we have to try to also solve one or two problems, and then we have to move to our next topic for cyclic group. So we begin with the first problem is this: let G be a fixed element of a group G, and if H is equal to A belongs to G, A G square minus is equal to G square A, and K we take another set, A is the element of a G, G A is equal to A G, then we have to show that this H is a subgroup of a G and this K is a subgroup of this H. So we have two questions. We have to show that G be a fixed element of a group G, then H is a subgroup of a G, and this K we define is a subgroup of a H. Clearly K is a subset of this H, and H is a subset of we have to assuming into the form of a G is there. So let's see, AB is the element of H. So if A and B are the element of H, then clearly AG square is equal to G square and BG square is equal to B square G by the definition of this, because all the elements of H is the form of AG square is equal to G square A. So if we take any two elements AB, then this should be H. This means AG square G square A and B G square G square B. So we have to starting from AB because we have to show that under this is a subgroup of a G. So we can show that A and B of G square is equal to, we have to show that G square AB, and we have to show that suppose as A inverse G square is equal to G square A inverse for all this satisfied into this scope. Clearly you have to just say that is a non-empty, because identity element is belongs to the H, and H is clearly is a non-empty. So A E into G square is equal to G square is E is satisfy this. So now we have to start from the ABG square, and now ABG square means we have used the condition of associativity, A of BG square, and BG square is equal to, you have a G square B. So we have to write A G square B, and G square B can be G square B, again using the associativity here we can write the A square G, and then A square G we have a G square A, so G square A. So we can say that AB belongs to the H for all A B belongs to H. So whenever A and B are the element of H, we have to show that this is AB is also belongs to H. So now second is we have to take in the inverse. So we take a G square inverse can be written as a G square A ka inverse, and then we can say that sorry, this is not equal. So this is G square inverse into A inverse is equal to, we can write the A inverse and then G square inverse, this is a product, okay. And then we have this is by the property, we use this property, A B ka inverse is equal to B inverse and A inverse. So this is G square ka inverse, G square ka G to the power minus 2 A inverse, and then we have A inverse G to the power minus 2. This implies that A inverse G2 is equal to G2A. So we can say that because you have to, G is the element of a group, so inverse, so G square is equal to A inverse G square is equal to G square A inverse. It means A inverse is the element of a H, we have to show that. So therefore H is a subgroup of a G. So first part of this we have to complete it. We have to show that if we have a AB G square is equal to G square AB is closed, and also inverse is also exists there. Now I leave this exercise as a you have to verify, because K is a subset of this, and then show that K is a subgroup of a H. This is a, I have to show that as a assignment for you. Then you have to try this. If verify K is a subset of H, and also show that K is a subgroup of a H. Now next example, we have to just say that we take H is the matrix of this A, B, 0, 1. A is not equal to 0, and A and B are the element of R. Is a subgroup of a multiplicative group of 2 by 2 non-singular matrices. We say that this H is a subgroup of a multiplicative group of 2 by 2 non-singular matrices, invertible matrices. We have to take a is a subgroup of a GL2R. Also we can say that this is a GL2. Here we composing this A should be not equal to 0. Why A not equal to 0? If A is equal to 0, then we have this matrix is equal to 0, and this matrix does not belongs to this. So this is not a subset of this thing. So that's why we have to imposing that A should be not equal to 0. Whenever A is equal to 0, then the determinant of this H is equal to whatever element is equal to 0, and if it is 0, this does not belong to the GL2R, which means this matrix is not a non-singular if the determinant is equal to 0. So we have to choose this restriction A not equal to 0 is a valid. So we have to prove that this H is a subgroup under the matrix multiplication. Let G be the multiplicative group of 2 by 2 non-singular matrix over R. So we have to show that H is a subgroup of a G. So clearly let A is the element of A1, B1 and 0 and 1 belongs to the H. A2, B2 is take A2, B2, 0, 2. Now condition is A1 is not equal to 0, A2 is not equal to 0, and B1, B2 are the any elements of a real numbers belongs to R. So B1, B2 is any elements belongs to R. So we have to take a, now find the B inverse. If you take A is B inverse is equal to this, then we have to calculate the determinant of a B. Determinant of a B is equal to, you have a A2, and A2 is clearly you have a not equal to 0. So now you have to just find the inverse of this. Inverse of this you have a 1 upon A2. Then we have to clearly write B inverse is equal to A2 inverse and minus B2 upon A2 of A. We have to take a adjoint of A upon determinant of A. B inverse is equal to now clearly we have to B is equal to, you have a this A2, B2 and I. So B is equal to, you have a A2, B2, 0 and 1, and then you have a B inverse, you have a A2 inverse minus B2 upon A2, 0 and 1. If you multiply it by this, you have a A2 inverse, and then you have a 0, then you have a A2 minus B2 upon A2, and then you have a plus B2, then you have a 0, and then you have a 1. And then clearly A2 inverse is equal to, you have a 1, and then you have a clearly this is equal to minus B2 plus B2 and 0 and 1, and then again you have a simply is equal to 1, 0, 0, 1. So this is clearly you have a identity matrix. So similarly we can show that into this form, A2 inverse minus B2 upon A2, and we have a 0 and 1, then we have to multiply it by A2, B2, 0, 1, then this can be written in the form of this into this, you have A2 inverse of A2, and then we have 0, then you have a clearly is equal to this A2 inverse B2, then you have a minus ka this is you have a A2 inverse B2, and then you have a minus ka B2 upon A2. So if we have to this is equal to 0 and you have a 1 is equal to. So this is again identity, and this quantity is again 0 because this is a A to B, this is cancelled. This is can be written as A2 inverse B2 minus B2 A2 inverse. This is A1 A2 are the real numbers, so this is cancel out. So this is again is 0 and 0 and 1, and this is again is a identity element is there. So we have to show that B inverse is equal to identity, and B inverse B is also identity. So that means this is clearly, this B inverse is the element of a GL2R. Then we have to just say that. Okay, so now we have to calculate what is our AB. So you have to A is equal to, you have a A1 A2 A1 sorry A1 B1 A1 B1 0 1, and then you have a B inverse, you have a this is we have to calculating for A and B. So A B inverse, so this is B inverse is equal to A2 inverse, you have a minus B2 upon A2 0 and 1. Then if you take a product of this, you have a clearly is equal to this form, A1 A2 inverse, then you have a minus ka A1 B1 A1 B2 upon A2 and plus ka B1 and 0 and 1. And now clearly you can see this the element of A1 is not equal to 0, A2 is not equal to 0. So clearly this is A1 A2 inverse is the element of a R, and this is element of a R whole, and this is R, so this is whole. The element is also belongs to the R, and that means this is the matrix of a type of this also belongs to the H clearly. So if this is belongs to the H, we can say that simply if this AB inverse is the element of H, so this clearly we can say that H is a subgroup of a G. And we have already shown that this H is a clearly non-empty, because we have a H is the type of a this, we have to take a 1 0 0 1, and this is clearly the identity element, and identity element is always belongs to the H. So this is clearly H is a non-empty. H is a non-empty, and AB inverse is also belong to the H. Then by the theorem of our criteria, we can say that if this H is a subgroup of a group of a G is there. Okay, now one more problem. Let G be prove that the G cannot have a subgroup of H with order of H is equal to n minus 1, where order of n should be greater than 2. Order of a G is equal to n, and this n should be greater than, strictly greater than 2. So cannot have a subgroup of H of order n minus 1. If a group of order, we have a group of order we have a giving is equal to n, and this n should be strictly greater than 2. Then we have to just say that if such a subgroup H does exist, then it must exclude exactly one element G from G. Since H is equal to greater than or equal to 2, we take a non-identity element H belongs to H. So strictly greater than, we take a greater, H should be greater than or equal to 2. So G, if it is greater than or equal to 2, then we have to just say that we just say that, so this is 3 minus 1 is equal to 2. So this is exactly greater than or equal to 2 elements of our H. So if order of H is greater than or equal to 2, so that means there is exact take a non-identity element, means there is at least one is identity element and another element is also. So we take a non-identity element H belongs to the H. So consider the element of GH. If GH is not belongs to H, if GH is not belongs to H, means what? Then GH should be is equal to G. If this GH is not the member of H, then what? GH should be the is a member of a G, and then GH is equal to is a member G. And by the cancellation property, H is the identity element, and which is a contradiction, because we have to assuming that this H is clearly not equal to identity. So clearly consider the element of a GH, we take two different elements of a G and H, and then clearly H by the cancellation property H is identity, and which is a contradiction. Now on the other hand, we have to, if GH belongs to H, if GH belongs to H, then we have to just say that GH is the member of a H and H is the member of a H, then H inverse is H, we have to H is the member of a H, then H is a subgroup, then H inverse is also the member of a H. So we can say that GH G inverse, GH H inverse, if GH H inverse is equal to, we have a G and G is the element of a H, again is a contradiction, because we have to show that G exactly one element G from G. So this means we can say G is the element of a H, a contradiction. So subgroups of H does not exist. This means we have to just say that the subgroup of H does not exist in this case is there. So clearly we just say that into this form we have to just solve these two problems. And now I have to move to the next topic, is a cyclic group. So we have to just define a cyclic group, and also giving you some few examples of a cyclic group. So let's start the definition of a cyclic group, and then we have to move give some examples of a cyclic group. We start with the definition of a cyclic group. Cyclic group, let G be a group and small g is the element of a G. If G can be represented as a G to the power n, means that is n times where n is some integers are there. So if G can be written in the form G to the power n is equal to G to the power n, means G, we have n times of a, take a G under binary operation, whatever binary operation we have as it. Then G is called as a cyclic group generated by this G, and it is denoted by this symbol. And then we have this left angle and right angles between this G, and this is G where G is called the generator. Means we have to say that we have to find in a group certain element which can generate whole the group. Means with this element can be write all the other elements of this G, then this such an element is exist, then we can say that this group is called as a cyclic group, and the element which generate the whole the group's elements is called the generator of this group G. For example, just one thing just say, because I just say G to the power n is equal to this G to the power n is equal to, we say that is n times is a binary operation. If the binary operation is multiplication, we can write in the simply this form. If the binary operation is addition, additively, then G becomes ng types, and this generator can be ng in place of G to the power n, we can write, and again G plus G plus G is a n times where n is a some integers there. So this generator of a G, or we can say that G can be simply G can be written in the form of a G to the power n. G to the power n with the product, and n times we have a whatever binary operation is, accordingly to binary operation this elements could be written into this form. Let us start very simple example. We have to just say that before example I just say one remark. From the definition it is clear that if G is generator of a G, then G inverse is also is a generator of this group, because if G is generated by G to the power n is this, and we take if a minus n, G to the power minus n, again n is the element of a G, and then we can say that G inverse to the power n, and G inverse to the power n means is generated by this. Means if an element is generated by G, then is also generated by its inverse. Generated by G, then also generated by the G inverse. So by the way, it is clear that if a group is generated by G, and then its group is also generated by the G inverse of this. For example, I just take a set of integers is a cyclic group. Under the addition, we have to say that one is a generator. Since if n can be written as n into 1, 1 into 1 we have to just write is a multiple of a 1. So n into 1 means here is we have to write a 1 plus 1 plus 1 is n times. So if we take a write a set of integer 1, we have a 1 square is equal to 2, 1 to the power 0, 1 is equal to 0, 1, and then we 1 ki power 1 is equal to, this is 0, this is 1 ki power 1 is equal to 1, 1 ki power 2 is equal to, you have a 1 plus 1 is equal to 2, 1 ki power 3 means 1 plus 1 is equal to, you have a 3, and so on. So in this case we have to write as if as a 4, we can write as a 4 into 1, 4, 1 plus 1 plus 1 is equal to 4 times. If it is a minus 1, then minus 1 plus minus 1 minus, similarly we have to write into this form. So n is the belong to generated by, so z is generated by, so z is generated by 1, and z is also generated because inverse of a 1 is under addition is 1 plus minus 1 is equal to 0. So if G is a generator, then by the remark we can say that G inverse also the generator of this group. So if we say that is 1 is this group Z is generated by 1, then Z is also generated by minus 1, then this can be written as a n can be written as a minus n into minus 1. So this means we can simply say that if Z is a 2 generators 1 and minus 1. There is another, we cannot find any other generator of a set of integer, we cannot find any other element. For example, we take a 2 and we take a 2 to the power 1 is equal to, you have a 2, we take a 2 square, we have a 4, then we have a, we cannot take a sum of a power is equal to, this is 2 to the power minus 1 is equal to, you have a like this. So we just say that clearly, we just say into a this form, this only 1 and minus 1 are the generator of a this group Z. Suppose Zn we have to taking into Zn. So Zn is the element of a, you know, that is 0, 1, 0, 1 up to n minus 1 for all n greater than equal to 1 is a cyclic group under addition modulo n. Now we have to find a generator. Given R Zn, and R can be written as R into 1, so is a multiple of a 1, so R is a belong to the generated by 1, so Zn is a generator of a 1. If because is generated, whole the set is generated by modulo 1, so is generated by 1, so Zn is a generated by 1. Now if a group, if G is any group is identity, only identity, and the generated by identity is a cyclic subgroup of a G. So this means is any group is identity itself, this is a clearly this. Now consider this group we have to just take it. So we have to consider the plus minus 1 plus minus I, the multiplicative group of a complex number of a fourth root of unity, and then G is a cyclic and generator. We try to find the generator. For example, is this I. So we take a I to the power 1 is equal to I, then we have a I square is equal to minus 1, I to the power you have a 3 is equal to minus I to the power 4 is equal to, you have a 1, and then if you have taken I to the power 5 is equal to I, then you have to again repetition is a start. So you have a, just say that you have a all the elements of this set are generated by this I. So this is I to the power 0 is equal to 1, I to the power 1 is equal to I square minus 1, I cube is equal to minus I, and then we have to again write in this one. So this means we have a again repetition is start. After I3 you take I to the power 4, I to the power 4 is equal to minus I into I, so is equal to, you have a 1 is there. So this is I to the power 5 you taking, I to the power 5 is equal to I to the power 4 into I, so 1 into I, you have a I is there. So in this case G can be generated by this thing. And now we just saw that if you remember, I will just say that in the remark, if G is a generator, then G inverse is also the generator. So inverse of I is has minus I, then minus I is also, we have a check easily this, minus I is also generator, minus I to the power 0 is equal to 1, minus I to the power is equal to minus I to square is equal to minus 1, and then 3 after this is equal to this, and then whole thing G is generated by this. So clearly we find there is a two generators of this group. one is a I, another is a minus I. Now we check 1 is the possible is a 1. So 1 to the power 0 is equal to 1. 1 ka square is equal to, you have 1 to the power n is equal to 1. 1 ka square is equal to 1 and so on. That means this is a repetition, all this thing is equal to there. So we can say that this is clearly is not a 1 is not a generator of it. Similarly, we can say that minus 1 is not a generator. So we can find this is a generator and minus I is also the generator of this, means a cyclic group. So this clearly is a cyclic group. A cyclic group may have more than one generator. So however, not all the elements of a G need to be generator. We can say that, however, not all the elements of a G need to be generator. For this example, we have I just show that is a I and minus I are the generators, but you can just check minus 1 is 1 and minus 1 is not equal to G, so minus 1 is not a generator for this group. Clearly, we can say that also 1 is also is not a generator of a this group. You have to take a 1 whatever power of 1, you cannot getting the I into this form or minus I into this form. Now one more example and then I have to stop this today lecture. Let group G7. Now G is equal to U7. Now you know that the U7's elements are 1 and then is relative prime to 1, 2, and then we have to just say that 3 to the power 0 is equal to 1, 3 to the power 1 is equal to 3, 2, 6, 4, because you know that U7 is the element of this 1, relatively prime of a 7 is equal to 2, 3 is also 4, 5 and 6. These are the elements of this. Now I check 3 is a generator because 3 to the power 0 is equal to 1, 3 to the power 1 is equal to 3, 3 square is equal to, you have a 9, then the remainder is equal to 2, 3 to the power 3 is equal to, remainder is equal to 6, 3 to the power 4 remainder is equal to 4 and 5. Now you have a 1, 2, 3, all the elements of this and this is equal to G7. So 3 is a generator of this. Now we have to check what is the inverse of this in this group of a 3, then this is also the generator of this. Not 5, 5 is also the generator of a G because you just say that you can just 3 into 5 is equal to identity is equal to 5 into 3. So 3 and 5 are the inverse of each other. So we can simply say that if we have a 3 is a generator, then 5 is also the generator of this thing. But we take a 2 is not a generator. Why 2 is not a generator? Because we just say that 2 to the power 0 is equal to 1, 2 to the power 1 is equal to 2, 2 to the power 2 is equal to 4, then 2 to the power 3 is equal to, again you have a 1. So 2 to the power 3 is equal to 8 and the remainder is equal to 1. So is a 1, again the repetition is start, then 2 is generated only this element and then clearly this one. And the inverse of a 2 is equal to 4. So clearly 4 is also not a generator. This is so the 2 and 4 are not a generator of this group. So I just say that means we have to if a group there is a maybe more than one generators are there and we have to just one more example and then the multiplicative group of a G and write in the form of this 1 to 4 and so on 1 by 2 1 by 4 and so on. Now is a cyclic group with a generator 2 and 1. You can just take 2 to the power minus 1 is equal to 1 by 2 and then 2 to the power minus 2 is equal to 1 by 4 and so on, and then we have to getting 2 to the power 0 is equal to 1, 2 to the power 1 is equal to 2, 2 square is equal to 4 and so on. So this is generated by 2. Similarly, it is generated by 1 by 2 also. So this means this 1 by 2 and 2 are the generators of a this group G. So this G is a clearly is a cyclic group and this is a group under multiplication is there. So now I just stop here for today lectures, and in the next class we have to continue the cyclic group and we have to discuss some one or two more examples, and then we have to try to some properties of a cyclic group and then move to the order of a group into this form. Thank you very much.